Good morning, students. In the last class, we discussed about the photoelectric effect, that is, starts with the experimental study and the wave nature with the photoelectric effect. So, what is photoelectric effect? That is, when a light of suitable frequency which falls onto the metals, the electrons absorb the energy, that is, of the minimum frequency, it absorbs the energy, and electrons are escape out from the metal surface. That phenomenon is called as photo emission, and the effect is called as photoelectric effect. So in the previous classes we studied about the experimental observation of the photoelectric effect. So in the today's class we start with the Einstein's photoelectric equation. So in the previous classes, we discussed about the experimental study of the photoelectric effect. So there were no equation related to the photoelectric effect, that is in the mathematical form. Only the experimental methods and the given in the theoretical explanation, right? So here Einstein first time gives the mathematical relation for the photoelectric effect. So that one we call as photoelectric equation, right? So in the year 1905, Einstein gives the new approach of the photoelectric effect. So according to the Einstein's theory of the photoelectric effect, that is, Einstein gave the theory in a different manner to that of the previous experimental observation. So he considered the light which falls onto the metal surface, that is the energy absorbed by the electrons, that is photoemission, that does not take place continuously by absorbing the energy of the radiation. So he mentioned the first point is that photoemission does not take place by continuous absorption of energy from radiation. So in the previous study we discussed about the when a light which falls onto the metal surface. If we consider this one metal surface, when the light which falls onto the metal surface, the energy absorbed by the electrons which are present in this metal, then the electrons will come out from that surface. So that one we call as photoelectric emission. So according to the Einstein's theory, he says that photoemission does not take place by continuous observation of the energy from the radiation. So this one is the first point. So according to the Einstein, he says that it does not take place, that is the emission of the electrons which does not take place by continuous observation of the energy to the electrons. So if we here we have the electrons, means here this one is the energy of the incident light. So this one is the first point. According to Einstein's theory, photoemission, that is the emission of the electrons, does not take place by the continuous absorption of the energy from the radiation. So for that he tells that the radiation, so that is this radiation is built up of, so he again says that the radiation is built up of discrete units of energy, right? So again he says that in the first he says that the photoemission does not take place by continuous absorption of the radiation. So for that he says that this radiation is built up of the discrete units of energy, right? So discrete unit nothing but the packets of energy, right? So those several packets of energy combined together we get the radiation. So according to Einstein, he says that the radiation is built up of the discrete unit of energy. So he called this discrete unit of energy called quanta of energy of radiation, or simply he says that quanta, right? So he says that the radiation is built up of the discrete unit of energy, and this discrete unit of energy called as quanta of energy of radiation. That is discrete unit nothing but packets of energy, right? So this one we call as packets of energy. The radiation of the incident light, which is built up of the several quanta of energy, right? So that one discrete units, he called that as quanta of energy, right? So these are the 2 points initially. By using this point, that is quanta of energy, by using this one, so Einstein used the photoelectric effect and photoelectric equation. So each quanta of energy, each quanta of energy of radiation has energy that is equals to h nu, where nu is the frequency and h is the wave. H is called Planck's constant and nu is the frequency of incident light, right? So the radiation is built up of the discrete units, that is packets of units of energy. Those packets of units of energy he named as quanta of energy. So each quanta of energy has the energy that is h nu. For example, if we have one radiation like this is the light radiation, means this radiation consists of discrete units of energy, that is it has number of units of energy. So each unit, that is this one called as quanta, then this quanta is has the energy value h nu. So here this quanta has the energy h nu. So here we have the h nu. So each radiation consists of discrete units of energy, that is packets of energy. So packets of energy combined together we have the radiation, right? So by using this quanta, Einstein explains the photoelectric effect and he used the relation of the photoelectric equation, right? So more important point is this one is the quanta of energy, right? So first he assumed that the photoelectric emission does not take place by continuous absorption of the energy from the radiation. Radiation is nothing but the incident light, that is electromagnetic radiation, because light consists of the electromagnetic radiations, right? Next, the radiation, he told that here, that is continuous absorption of energy, that is photoemission, that is electrons will not absorb the radiation continuously. Hence, for that to overcome, he says that this radiation is built up of discrete units, that is small units, right? So that one we call as quanta. So each quanta has the energy that is h nu. So he given the energy h nu, right? So when h is the Planck's constant and nu is the frequency of the incident light. So by using this quanta of energy, Einstein used the photoelectric effect. That is the theory of the photoelectric effect. So according to this theory, considering here one metal. So this one is the metal plate, right? So metal plate consists of the electrons. So it has several number of the electrons, right? So denoted by e to the power of minus. So according to the Einstein's photoelectric effect, the incident light, So this one is the incident light, that is quanta of energy. So this radiation consists of the quanta of energy. So this quanta has the value of the energy is how much? That is h nu, right? The radiation, the incident quanta, the radiation which falls onto the electrons, it has the energy that is h nu, right? So this h nu is the energy of this quanta, right? That is packet of energy. So this electron absorbs this energy, right? So in the initial we discussed about that the electrons which are not come out freely. So these are the free electrons which will not come out easily from the metal surface because due to the attractive force between the positive and negative charges. So if this electron gains the minimum energy, then these electrons break up the force of attraction between the opposite charges, then these electrons will come outside. So that minimum energy we call as work function, right? So here also same will happen. So the energy of the incident quanta, that is h nu, which falls onto the metal surface, the electron absorbs the energy, right? So this in this energy, some part of the energy is absorbed by the electron to escape out from this metal surface. So that one we call as work function. So out of this energy h nu, some part of the energy is absorbed by the electron. So how much part of the energy is absorbed? Nothing but minimum amount of energy which is needed to escape out from this metal surface. That is from here to here, right? So that minimum energy we call as pi naught. So what is pi naught? So pi naught is called as work function. So what is work function? The minimum energy required by the electron to escape out from this metal surface. So that energy we call as work function, right? So out of this energy h nu, some part of the energy is utilized to escape out from this surface. That is the minimum energy. So that energy is the work function, right? So some part is absorbed here and remaining some part is utilized to escape out from this metal surface with the velocity. So velocity, it travels out with the velocity is nothing but it has kinetic energy. Right? So according to the Einstein, when an incident radiation of the energy h nu is absorbed by the electron, that is in the metal surface, some part is utilized to escape out from this metal surface and the remaining part is utilized for the kinetic energy. So this one is explained by the Einstein, right? So here h nu is the energy of the incident quanta, right? So out of this energy, some part of the energy is absorbed by the electron to escape out from this metal surface. So that is pi naught, and the remaining is utilized for the kinetic energy, right? So here if we say that E is equals to pi naught, that is energy which is equals to sum of these two energies, that is one is kinetic energy and another one is work function, right? So this one is the Einstein's photoelectric effect. So according to Einstein's photoelectric effect, when a radiation of energy, that is incident quanta of the energy h nu, which falls onto the metal surface, some part of the incident energy is utilized for the minimum energy required to escape from the metal surface, or directly we say that utilized as the work function, and remaining part is utilized for the kinetic energy of the electron, right? So this is the Einstein photoelectric equation. So if we write in the equation form, then here energy of incident quanta, energy of the incident quanta, that is equals to, Here we have the work function plus here we have kinetic energy, right? So this is the photoelectric effect according to the Einstein's theory. So according to Einstein's theory, the energy of the incident photon is absorbed by the electron, that is, it absorbs minimum energy to escape out from the metal surface, and the remaining energy is utilized for the kinetic energy of the electron, right? So if the electrons are closely bonded, so this energy is called as maximum kinetic energy. So if the electrons are closely bonded, then here it needs more energy. So understanding here the electrons are closely bonded, so the work function is more, hence the kinetic energy is less compared to that of the maximum kinetic energy, right? So if the electrons are closely bonded, then the work function will be more because it absorbs more energy to escape out from this metal surface. So work function is more, then we have the less kinetic energy compared to this maximum kinetic energy, right? So this one is the one point. That one is, if the electrons are closely bonded, the work function is more. That is, work function nothing but the energy required to escape out from this metal surface. So more energy is absorbed, then only less amount of energy will come outside for the kinetic energy. So less energy is the less kinetic energy compared to this maximum kinetic energy, right? So this energy of the incident quantum, that is, we can write that one as h nu, that is equals to work function is we denoted by pi naught plus this one is the maximum kinetic energy, that is K maximum, right? So here the Einstein's photoelectric equation can be written like this: h nu is equals to pi naught plus K maximum, or K maximum is equals to h nu minus pi naught. So this one is the photoelectric equation, right? K max is equals to h nu minus pi naught. So by using this equation, if we define the photoelectric effect, then we have the statement in photoelectric effect, the electron observes incident quantum of energy, that is h nu, right? So in photoelectric effect, the electron observes the incident quantum of energy h nu of radiation if the this quantum of energy, this quantum of energy observed, if this quantum of energy is observed exceeds the minimum energy to escapes minimum energy required to escapes from metal surface. So that is the work function pi naught, right? So in photoelectric effect, the electron absorbs the incident quanta of energy h nu of radiation. If this quanta of energy absorbed by the electron, so here absorbed by the electron exceeds minimum kinetic energy required to escape from the metal surface, then electron escapes out with maximum kinetic energy. Right? So this is the Einstein's photoelectric effect. So according to Einstein's photoelectric effect, that is in photoelectric effect, the electron absorbs the incident radiation. So this one, if we consider here, this is the metal plate. So here we have the electrons. Then here it is H2. This electron absorbs the quanta of radiation. So this one is absorbed by the, this quanta of energy is absorbed by the electron. So how much energy is absorbed means that is absorbed by the electron exceeds the minimum energy. That is, it has absorbed that it is to escape out from this metal surface. That is from here to here, right? So that is exceeds the minimum energy required to escape out from the metal surface, or directly we say that one as work function. Then electron escapes out with the maximum kinetic energy. So this electron will escapes out with the maximum kinetic energy, and we given the maximum kinetic energy is equals to h nu minus pi naught, right? So this one is the Einstein photoelectric equation. So this is the Einstein photoelectric equation. Now we will discuss on Einstein's photoelectric equation. So by using this equation, we will discuss few this is Einstein's photoelectric equation, that is K maximum, that is kinetic energy maximum, that is equals to h nu minus pi naught, right? So by using this equation, we will discuss the few points. So in this first one, so pi naught we call as the work function. So here I will write where K max is the kinetic energy, h Planck's constant, nu frequency of incident radiation, next pi naught work function, right? Now we will discuss one by one, that is kinetic energy maximum is equals to the incident photon, that is incident quanta of energy, that is h nu minus pi naught, that is work function. For every metal has a different metals have a different pi naught value, so that is pi naught is constant for a particular metal. So as we discussed with this work function in previous, that is platinum, for different metals have different work function, hence this work function is constant for a particular metal. If we consider any one particular metal, then for that particular metal this pi naught becomes constant, hence the kinetic energy relates with the h nu, where h is also a constant, that is h is the Planck's constant. Then we have the relation, that is if for a particular metal pi naught is constant, so different metals have different values, then this value will not change, that is this pi naught value is remains constant. Hence if we write the relation, means k maximum is equals to h nu, that is k maximum is relates with the nu, because here h also what, that is the constant, that is Planck's constant. So if we write this relation, then kinetic energy of the electron is proportional to the nu, that is frequency of the incident radiation, right? So this one is the first point. So first point is the observations of the photoelectric equation. So according to this, pi naught value is constant for different metals, right? For each metal have each pi naught value, so pi naught is constant, h is constant. Then kinetic energy of the electrons depends only on the frequency of the incident radiation, so that can written as k max is proportional to nu, that is k max is varies linearly with the what, this one is the frequency of the incident radiation, right? So as this one we observed, explained in the experimental observation, that is the energy of the electrons directly depends on the frequency of the incident radiation, and it is independent of the intensity. So it is independent of intensity. So this one is the first point, right? Next, the intensity is measured. So the intensity of the incident light is measured by, so here if you consider this is a metal, the radiation is falling onto the metal plate, then the intensity is measured, that is how many number of quantas are incident on this metal plate per second. So intensity is measured by number of quantas incident per second, right? So the intensity is measured by the number of quantas which are incidenting on this metal surface per second. So for 1 second, how many number of these packets of energy is incident on this metal surface? So that will says that as the intensity of the incident light. So if the number of quantas which are incidenting on this metal surface is more, that is intensity is more, right? So if we increase the intensity, then the number of quantas which falls onto this metal surface is more. So if the quantas are more, then the electrons which are emitted is more, right? So here the electron emitted per second is more. So if electron emitted per second is more, then we say that electron emitted per second we call as photo current. Then we say that intensity is proportional to the photo current, right? So if we increase the intensity. So if we increase the intensity, the number of quantas also quantas per second also increases, and hence number of electrons emitted per second also increases, right? So if we increase the intensity, so intensity is measured by the number of quantas which falling on the metal surface per second. So that is how many number of quantas which falling per unit second. If we increase the intensity, then the number of quantas which falling on the metal surface also increases. So if the quantas are increasing, then the number of electrons which are emitted out from the metal surface is also increasing. So this one we call, that is electrons emitted per second, we call as photo current, because current is charge per unit time. That is, here the electron is the charge per unit time. We say this one as the photo current, because here the photo electrons are emitted, hence we call this one is photo current. So we directly say that photo current is proportional to intensity of incident light, right? So this one is the second point. So first point is the kinetic energy is proportional to the frequency of the incident light, and it is independent of the intensity, because the intensity depends on the number of quantas incident per second, right? So number of quantas incident per second, if the number of quantas are incident per second means the electrons emitted per second also increases, then the photocurrent is proportional to the intensity of incident light. So this symbol is proportional, that is Kmax is directly proportional to the frequency and photocurrent is directly proportional to the intensity of incident light. So this one is the first point. So from the first point we say kinetic energy depends on frequency, and here the second point, photocurrent depends on the intensity of the incident light or incident radiation, right? So next, for the third point, so third point, this can be written as kinetic energy maximum is equals to h nu minus work function, that is pi naught. So pi naught can be written as this pi naught is equals to h nu naught. Nu naught is the threshold frequency. So above this frequency the photo emission takes place. That is the minimum frequency which has to falls onto that metal plate. Then that one is also called the work function. Hence we write work function is equals to h nu naught. Now if we substitute here h nu naught. So in these two we have the common is h. So if we take h common, we have the relation h is equals to nu minus nu naught, right? So nu naught is the threshold frequency and nu is the frequency of the incident light. Either it may be greater than nu naught or it may be less than nu naught. So what happens if nu is less than nu naught? So if we observe here nu minus nu naught. So if nu is less than nu naught, for example the frequency here nu is 10, which is less than nu naught is 50, right? So considering nu naught as 50 and considering nu is 10. Now if we substitute here 10 minus 50, then what we get in minus 40, that is minus some new value, that is the kinetic energy is negative. So by this, if nu minus nu naught, that is nu is less than nu naught, then kinetic energy, that is maximum kinetic energy, is negative. That is maximum kinetic energy is, so this value is negative. So this value is negative, nothing but there is no photo emission. There is no photo emission. So we are discussing the points which based by using the relation, that is photoelectric equation given by the Einstein, right? So this work function can written as h nu naught, right? In these two terms we have the common h, so nu minus nu naught. The condition is if the incident frequency is less than the threshold frequency, then this kinetic energy is negative. So if the kinetic energy is negative, nothing but there will be no emission of the electrons. So only positive kinetic energy, then it has the velocity to escape out from the metal surface. That is kinetic energy, we know kinetic energy is equals to half m b square, right? So this kinetic energy is negative, means there will be no negative mass, then the velocity is negative. So velocity is negative, nothing but there will be no emission of the electrons out, that is the electrons has no velocity to come out from the metal surface. So this one is the third point, right? So if nu is greater than nu, then the kinetic energy has positive value, then there will be photo emission. That is the frequency which is greater than the threshold frequency, then only the photo emission takes place, right? So next, in terms of potential, that is stopping potential or retarding potential. So in the experimental study, we studied the kinetic energy is equals to the work done. That is, work done can be written as, from the work energy theorem, change in kinetic energy is equals to the work done. So this kinetic energy can be written as E V naught. So in the experimental study, we discussed K maximum is equals to E V naught. So in the previous experimental study, we discussed K maximum is equals to E V naught. That is the work done by the electron when the potential is given, that is the stopping potential is V naught. So from work energy theorem, the change in kinetic energy is equals to the work done. So work done can be written as E V naught. So E V naught is equals to h nu minus, keeping this one, that is pi naught as is, right? So we need the relation for the stopping potential V naught. Then if we shift E to the RHS, then it becomes V naught is equals to h divided by E into nu minus pi naught divided by E, right? So this one is the fourth observation, right? We have the equation, so rearranging here. So in place of K max, we written E V naught, that is equals to h nu minus pi naught. So here observe, pi naught is a constant value for an individual metal. For each metal have different pi naught values. If we consider one metal, then that for that metal pi naught value is constant, right? So this value is constant, h value is also constant, and E, where E is the charge of the electron. So this value is also constant, 1.6 into 10 to the power of minus 19 coulomb. So this value is also constant. Now if we shift this to RHS, then becomes h divided by E into nu minus pi naught divided by E. So if we observe here, so this value is constant, pi naught constant divided by constant, we get the constant value only. right? So here h divided by E is also constant. Then V is, that is V naught is directly related with the nu. So this means that V naught varies linearly with the nu. That is V naught is proportional to nu. We can write like this: V naught is proportional to nu. That means stopping potential is varies with the frequency of the incident radiation or incident light. So these explanations already we given in the experimental method. So by using here, so by using the photoelectric equation, Einstein's photoelectric equation, we are giving the same experimental in terms of these equations, right? So then this shows that the potential is proportional to, that is stopping potential depends on the intensity of the incident light. So this equation gives the straight line with the slope h divided by E, right? So if we plot the graph for here, we have the graph. So this one is the V naught and here is the nu. Then here we have the curve, right? So for this curve, this one is the slope. So straight line with the slope is equals to h divided by E, right? So this will either like this or it will be, this will be like here, right? So these 4 points we discussed in the experimental study. The same factors we are discussed by using this equation, right? So in that, photocurrent is directly proportional to the intensity of incident radiation, kinetic energy is directly proportional to the frequency of the incident radiation, stopping potential is directly proportional to the frequency of incident radiation, and the kinetic energy is independent of the intensity of the incident radiation. So one more point is, the fifth point is, the photoelectric emission is the instantaneous process, right? So here the collision between the radiation, that is quanta, and to that of the electrons, because in incident on the electron means there is a collision of this quanta with the electron. So here the collision is elastic in nature, so this collision is very spontaneous, so hence the emission of the electron is also spontaneous. Then we say that photoelectric emission is instantaneous process, right? So these are the 5 experimental, Einstein's photoelectric observations. So we need to know what are the experimental observations and photoelectric equation observations, right? So here the fifth point is, due to the collision between the quanta and the electrons, so the collision is elastic in nature, hence the emission of the electron are spontaneous. So electron collision is spontaneous, that is elastic collision, hence the electron emission is also spontaneous, hence the photoelectric effect is spontaneous, right? So this is about the Einstein's photoelectric equation. By using this equation, we discussed the 5 parameters, right? So one is kinetic energy, one is stopping potential, and another one is photocurrent with the intensity, and next, first one, that is intensity, right? So this one is the V naught is equal to h by E is the constant into nu minus pi naught by E, right? So this is about the Einstein's photoelectric equation. So this one is also important for 3 marks. So if we ask the, explain the Einstein's photoelectric equation observations, or explain Einstein's photoelectric effect, means you have to explain all these 4 points. Out of 4, you can explain any 3 of these points, right? So in the next class, we will discuss about the particle nature, right? Thank you.